Greetings. In last lecture, we were discussing about the subject structural mechanics 2, in which we have taken an overview of the course defined by university, and then we have gone through the evaluation methodology prescribed by the university, as well as we have gone through the syllabus content of the subject. Then we started our discussion with reference to the prerequisite required for the structural analysis, where we come across the performance expected from the structure. Then we'll learn about the various types of loads which are coming on the structure. Today we'll start our discussion with reference to the classification of a structure. The classification of a structure is based on dimension or the way they carry the loads. Based on dimension, the structure is classified as a one-dimensional element, two-dimensional element, and three-dimensional element. One-dimensional element, say length is very large compared to the other two dimension. Means what? Here we are going to neglect the effects of the forces along the other two dimension. Only one dimension is being under consideration. For example, in case of a beam, we consider the effect of load along the longitudinal length, and we assume that beam is subjected to flexural load only. That's why we neglect the forces, stresses, strains which are coming across the cross section of the beam. In the same way, frames, trusses. In case of trusses, we assume that the truss members are axially tension member. We neglect the stresses which are developing across the cross section. We consider that the force is concentrated along the centroidal axis. In the same way, cables, arches, and bars. These are the example of one-dimensional element. Though they are having a 3D geometry, but we are going to consider them as a line element or one-dimensional element by neglecting the effect of other two-dimensional element. Here length and breadth are large compared to the thickness. Means here the thickness is being neglected. For example, slabs, we concentrate on the loads which are coming on the surface area of the slab, irrespective of the whatever the forces has been developed along the thickness of the member. So here we are going to take the effect of the forces, stresses along a planar geometry. Then we are going to call it as a two-dimensional structure. When in case of three-dimensional structure, all three dimensions are equally prominent. Example, foundation, retaining wall, and gravity dams, where we consider the effect of all forces on all three mutual direction. Based on the way they carry the loads, the structure is classified as a beams. Beams carry their loads by developing bending moment and shear force at different section. So here we consider that a beam is being subjected to a load. Predominantly they are the flexural load, thereby developing the bending moment across the span as well as the shear across the length of the section. In case of trusses, we consider trusses as a axial forces, axially loaded element, which carries only the axial force. Either it may be axial tension or either it may be axial compression. When we talk about the plane grid, in case of plane grid, we consider the plane grid is going to be subject towards the bending moment and shear and twisting also. So here the members may be subjected to the bending based on the geometry. It may have a location of what we say twisting action along the planar geometry. In case of arch, we consider they are the predominantly subjected to the bending moment, radial shear, and normal thrust across the cross section. We consider that as a thin line element having a profile, arch profile. Okay, next to that there is a cable. In case of cables, we consider the members are subjected to only axial tension only. So they are predominantly carrying tensile forces. Thin plates, we are going to consider these thin plates are subjected to the bending and twisting. Here the bending will be along the surface area, whereas the corner it will be subjected to the twisting forces. Next category is the thin shells. In that mainly they are going to subjected to the membrane stresses. The curvature of the body is and the thrust which are going to apply across the thickness is going to consider. We call that type of section as a thin shell section. Let's move towards the discussion on types of supports. We have roller, hinge, fixed, elastic, and guided supports. Why we provide this support? These supports provide the restraining and constraints to the structure. Restraining condition and constant to the structure. For example, in case of roller support, it restrains the displacement along the normal towards the plane on which roller is going to move. If it is perfectly horizontal, it may have a normal here restraint along the displacement along the normal direction with reference to vertical axis. When it is inclined, then it will have a normal thrust with reference to the inclined surface. Now it also provides some forces. It also develop some constant condition, like it develops one reactive forces which is normal to the plane on which the roller is moving. Okay, that is we call as a normal thrust. In case of hinges, in hinge it restrains the linear displacement in any direction. Linear displacement in any direction means if we are having 2D geometry, so we will have two planes here, x plane and y plane. So it will not allow the linear displacement of this body in x and y, thereby it will restrain. In similar way, it will provide two numbers of the forces, one normal to the plane and one parallel to the plane, means here one vertical and one horizontal if we consider two-dimensional geometry here. In case of fixed support, uh, it will restrain the displacement along linear as well as angular direction, means it will neither allow the member to move in the respective axis linear direction, as well as it will not allow the member to rotate along its axis. Okay, thereby it's going to develop a three reaction forces here. Let us say these reactive forces are Rx, Ry and Mx in reference to the 2D plane. Rx with reference to x direction, Ry with reference to y direction, and movement along any of the direction should be M. Elastic here the support is being put on a predefined uh, uh, stiffness member. Let us say here the spring is there. It will have predefined capability to get deformed. Okay, that's why it will have partial restraining of the linear displacement. It will allow the displacement, but it will have partial restraining of the linear displacement. Thereby, it is going to develop a one reactive forces which is on the virtue of the load carrying capacity of this elastic system. Guided supports, neither it will restrain, neither it will have any reactive support, only it will provide the motion in the predefined directrix. Let us go towards the equilibrium conditions. We know that there are translation equilibrium condition like summation of x equals to 0, summation of y equals to 0, and summation of z equals to 0. Similarly, we have rotational equilibrium equation available here. In case of 3D, we will have summation of moment in x direction equals 0, summation of moment in y direction equals to 0, and summation of moment in z direction equals to 0. When you want to put this this equilibrium condition in terms of uh, vector format, then the resultant can be represented as fr, means it's going to, with reference to normal to the plane, will be equals to fxi plus fyj plus fzk equals to 0, where ijk will represent the direction cosine in respect to the xyz coordinate system. In similar way, we can have the moment equilibrium along the reference plane as a mxi plus myj plus mzk is equals to 0. Now, let us discuss about the types of material. So, in case of a structural design, we come across various type of material which has different properties, like isotropic in nature, where properties are same in all direction. For example, mild structural steel, aluminum alloy, high strength metals alloy, glass. The second type of material is orthotropic, where properties are different in mutually perpendicular axes, like we have the case of fiber reinforced composites. Then anisotropic material, properties different in all directions. Like for example, timber. Homogeneous material properties are same in all points. It is due to virtue of the composite of the material, for example, stones and bricks. And heterogeneous material, it's a complex geometry, a combination of various material binded together. That's why properties are different at different points. For example, timber, soil. Let's talk about the material characteristics which we have to need to be reviewed before going for a structural analysis. For structural analysis, we need only few material properties like Young's modulus, Poisson's ratio, coefficient of thermal expansion, and density. All this depends upon the behavior of material. So very first behavior which we are going to see here is a linear elastic behavior. What's the meaning of linear elastic behavior? Here there is a proportionality between the applied stress and applied load versus deformation of the member. So they will have a linear relationship. When we apply a load, they will show the linear relationship up to a elastic limit. When we remove the load, they will follow the same path to have a removal of the stresses or a removal of the deformation. Then such a material is going to call as a linear elastic material. Linear inelastic material means here material is going to going to take the stress in a linear fashion, where there is a small increment in the stress, there will be proportionally increment in the strain, and this behavior will continue up to the elastic limit. When we unload this material, the material will regain its original state, but it will follow the different path. It will not follow the path from the during the stressing. It will follow the other part to get a reversal of the deformation or the loading. So such a material is called as a linear inelastic material. Now there are other two forms here: non-linear elastic material and non-linear inelastic material. The behavior is from initial to the last, it's non-linear. There will be no proportionate sign between the applied forces versus the deformation gained by the member. But it will have the same when the loading is being removed. It will have the same path. It will trace the same path as it has trained during the loading. Then we call it as a linear elastic material. Vice versa, we will call it as a non-linear elastic material. Amongst this, the very important part is that your material should be an elastic material. So here, what is the meaning of elastic material? Here, material should behave as a Hooke's law. So if the material doesn't behaves according to Hooke's law, then we are going to say the material gone to the plastic zone, and in the plastic zone, the properties of the material will be vulnerable. That's why if I want to stress up the material for structural analysis, I have to take the properties of the material properties in reference to the elastic nature only. Okay, let's move towards the type of internal stresses developed because of internal forces in the structural member. So here my members are subjected to various loading condition, as we have already stated. Due to this loading condition, there may be axial force developed along the section or axial force in tension or compression. Thereby it will introduce the stresses like direct tensile stress and direct compressive stress. In similar way, the material may be subjected to bending moment. This bending moment will give rise to the bending stress. This bending stress may be ideal tensile bending stress or compressive bending stress. Let us take an example of beam here. Typical example of a beam here. Here beam is subjected to point load. What will happen? The supports the beam is being loaded along the its length. That's why it will get buckled down. The bottom fiber will observe the tensile stress, whereas the top fiber of this beam will observe the compressive stresses. Okay. Next to that, the material will be subjected to a shear force, thereby developing the shear stresses. These shear stresses may be along the cross section, or it may be across the perpendicular to the cross section or parallel to the cross section. We call it as a shearing stress, and we call it as a what we say normal stresses or shearing stress along the member. Twisting moment. This twisting moment will also develop a shearing stress and balance forces along the section. Thereby there may be a cross cut for the cross section. It depends upon the modulus of rigidity of that particular section. Okay. Now we'll go towards the basic principle, which is said to be a pioneer principle for the development of analysis of determinate structure. The principle of superposition. What this principle states? The statement here: the total displacement or internal loading stresses at any point in a structure subjected to several external loading can be determined by adding together the displacement or internal loading, that is stresses caused by each of the external loads acting separately. Means here, if suppose we are going to consider the total displacement of a member which is subjected to a given loading combination, then the deflection observed by this system will be equal to the displacement or internal displacement which is caused by external force when we look it in a individual pattern or by separation. So for example, let us say this beam is there which is subjected to a typical load combination as shown in figure. The beam is subjected to UDL up to a certain span, and at one end there is a moment. This become a complex geometry. If I want to ascertain this the vertical displacement at this complex geometry, I have to work rigorously. So what I can do? I can simplify this problem by separating these two into two separate cases. One, the beam is subjected to the UDL only. The second one, beam is subjected to the moment. Thereby I can superimpose the static relationship and get the answer, and the answer should be that Vx is equals to v1x plus v2x means the